Hello, welcome to this Open Systems Media webinar on designing with ultra-low power real-time clocks. I'm Mike Demler, Editorial Director for Open Systems Media's DSPFPGA.com website, and for our monthly Tech Brief newsletters that cover those technologies, as well as covering topics like Android, EDA, and LTE. I will be serving as the moderator for today's webinar. I'd like to start with an introduction to our topic today. Designers of systems that require timekeeping functions are often challenged by the constraints of limited printed circuit board space and low power budgets. In this webinar, you will learn how incorporating a small footprint real-time clock can help to overcome these issues. Our speaker will explain what a real-time clock is, and go over some of the features and benefits that such devices can provide for your system, and then describe some example applications. Before we get started, I have just a few housekeeping items. Today's presentation will consume approximately 50 minutes, leaving us 10 minutes or so for questions at the end. There are a few on-screen buttons that I'd like to bring to your attention. First, the Enlarge Slides button. By clicking on this button, you'll be able to view the slides in full screen mode. You should also be able to find a button that allows you to download a copy of the slides. There's a Forward to a Friend button. You can use that to send an email to a colleague and invite them to join us for this event. You'll also find on your console window a button that allows you to enter questions in real time. We'll do our best to address your questions during the closing Q&A session. If you have a question pertaining to the webcast operation itself, one of our technicians will respond back to you during the presentation. We may not get to all of your questions before the end of our allotted time, but in that case, someone will get back to you after the webcast with more information. Finally, this webcast will be posted online within 48 hours, and an audio podcast will also be made available. We'll have more details about that at the end. So on to our presentation. Our speaker today will be Emmanuel T. Nana. Emmanuel is a product applications engineer with the Interface Products business line at NXP Semiconductors. He is primarily responsible for supporting industrial and automotive customers in the Americas with interface products from NXP. I'd like to hand it over to you, Emmanuel.
Thank you very much, Mike. Good morning, everyone. So today, as Mike said, we'll be talking about designing with ultra-low power real-time clocks. My name is Emmanuel Nana with NXP Semiconductors. For today's webinar, what we'll be talking about, first I would like to go over an introduction to real-time clocks. They will cover some basics about real-time clocks. Then we'll look at real-time clocks portfolio from NXP Semiconductors, and then narrow down to some of the low-power real-time clock devices that NXP do offers. And then we'll talk about some of the applications for these devices and development tools that NXP do offer for customers to help design in these products into the systems, and then we'll summarize. So let's begin with an introduction to real-time clocks, some of the basics to real-time clocks. So basically, what's a real-time clock? A real-time clock is an electronic device that keeps track of time in any electronic system the way humans would do. So it basically keep counts of the seconds, minutes, hours, and days. The time that we in our daily lives keep in systems. Also, sometimes we need to keep time in a similar manner to know what time certain events occur, or to be able to schedule events to occur at a certain time. Typically, a real-time clock will have a 32.768 kilohertz crystal that keep track of this time. And we'll talk about the devices that we do offer from NXP Semiconductors. Those devices will typically have an I2C or an SPI interface. This interface is used basically to communicate with the device so that the user can program the time, the current time in the device, or the user can read off the current time at any time, or the user can maybe set other parameters like alarm, interrupts and other features that we'll talk about later on in the presentation. On the next slide, basically, rationale for using
Hello, welcome to this Open Systems Media webinar on designing with ultra-low power real-time clocks. I'm Mike Demler, Editorial Director for Open Systems Media's DSPFPGA.com website, and for our monthly Tech Brief newsletters that cover those technologies, as well as covering topics like Android, EDA, and LTE. I will be serving as the moderator for today's webinar. I'd like to start with an introduction to our topic today. Designers of systems that require timekeeping functions are often challenged by the constraints of limited printed circuit board space and low power budgets. In this webinar, you will learn how incorporating a small footprint real-time clock can help to overcome these issues. Our speaker will explain what a real-time clock is, and go over some of the features and benefits that such devices can provide for your system, and then describe some example applications. Before we get started, I have just a few housekeeping items. Today's presentation will consume approximately 50 minutes, leaving us 10 minutes or so for questions at the end. There are a few on-screen buttons that I'd like to bring to your attention. First, the Enlarge Slides button. By clicking on this button, you'll be able to view the slides in full screen mode. You should also be able to find a button that allows you to download a copy of the slides. There's a Forward to a Friend button. You can use that to send an email to a colleague and invite them to join us for this event. You'll also find on your console window a button that allows you to enter questions in real time. We'll do our best to address your questions during the closing Q&A session. If you have a question pertaining to the webcast operation itself, one of our technicians will respond back to you during the presentation. We may not get to all of your questions before the end of our allotted time, but in that case, someone will get back to you after the webcast with more information. Finally, this webcast will be posted online within 48 hours, and an audio podcast will also be made available. We'll have more details about that at the end. So on to our presentation. Our speaker today will be Emmanuel T. Nana. Emmanuel is a product applications engineer with the Interface Products business line at NXP Semiconductors. He is primarily responsible for supporting industrial and automotive customers in the Americas with interface products from NXP. I'd like to hand it over to you, Emmanuel.
Thank you very much, Mike. Good morning, everyone. So today, as Mike said, we'll be talking about designing with ultra-low power real-time clocks. My name is Emmanuel Nana with NXP Semiconductors. For today's webinar, what we'll be talking about, first I would like to go over an introduction to real-time clocks. They will cover some basics about real-time clocks. Then we'll look at real-time clocks portfolio from NXP Semiconductors, and then narrow down to some of the low-power real-time clock devices that NXP do offers. And then we'll talk about some of the applications for these devices and development tools that NXP do offer for customers to help design in these products into these systems, and then we'll summarize. So let's begin with an introduction to real-time clocks, some of the basics to real-time clocks. So basically, what's a real-time clock? A real-time clock is an electronic device that keeps track of time in any electronic system the way humans would do. So it basically keep counts of the seconds, minutes, hours, and days the time that we in our daily lives keep in systems. Also, sometimes we need to keep time in a similar manner to know what time certain events occur, or to be able to schedule events to occur at a certain time. Typically, a real-time clock will have a 32.768 kilohertz crystal that keep track of this time. And we'll talk about the devices that we do offer from NXP Semiconductors. Those devices will typically have an I2C or an SPI interface. This interface is used basically to communicate with the device so that the user can program the time, the current time in the device, or the user can read off the current time at any time, or the user can maybe set other parameters like alarm, interrupts, and other features that we'll talk about later on in the presentation. On the next slide, basically, rationale for using a standalone real-time clock. So there are two basic reasons why in a system a user may want to use a standalone real-time clock. The two basic reasons are, number one, low power, and number two, accuracy. So typically, a microcontroller may have, so many microcontrollers do have real-time clocks integrated in them, but you find a lot of customers who still want to use an external real-time clock. And I said the first reason is basically because of power consumption. With an integrated real-time clock in a microcontroller, typically with the entire system shut down and the microcontroller in a low power mode and just the real-time clock running, the micro with just the real-time clock running consume somewhere in the microamp range of current. With an external real-time clock, and I will be talking about the NXP's real-time clock. NXP do offer devices that can go as low as 100 nanoamps in power consumption. So you find these devices being used in systems where power consumption is very important, especially like battery-operated system, where the system designer wants to maximize the power savings and allow the battery to be able to last for a very long period of time. And since the real-time clock is running all the time, it's very important that the real-time clock consumes as low power as possible. The second reason again for using a real-time clock is accuracy. There are some systems where the timekeeping function, the accuracy of the timekeeping function is very important. And in those systems, with a real-time clock function, the accuracy is really dependent on the crystal. So when using an external crystal, basically the timekeeping function, you are at the grace of the accuracy of the crystal. There are some real-time clocks, and we'll talk about those also in this presentation. There are some real-time clocks that have an integrated crystal within the real-time clock. And because that crystal is integrated within the device, the crystal is also temperature compensated, and so a lot of the accuracy that is due to temperature drift can be eliminated because of that. And by doing so, we can attain a very tight accuracy, and that's how we are able to improve the accuracy of the real-time of a standalone real-time clock by having the crystal integrated to it. So those two reasons are the most important reasons why we find so many customers using standalone real-time clocks. The other reasons, there are some other reasons also why you may find customers wanting to use a standalone real-time clock, and most of those is because of the additional features that some of these devices do offer. For example, an external real-time clock may have functions like watchdog functions, some additional power management functions, timestamp and external RAM and things like that. The watchdog function basically provide an additional safe bet for the system. So if in case the microcontroller locks up and the watchdog within the microcontroller is not it's also locked up, then the watchdog within the real-time clock can still wake the system and recover it from any failure that occurs. Then the additional power management features just help to eliminate additional components within the system. So some real-time clocks do have power management features that can be done within the real-time clock, and so that saves on additional components on the board. On the picture in this slide, basically I'm just showing how a microcontroller may have many peripherals around it, and one of those peripherals may be a real-time clock, and also showing that the real-time clock, in addition to the timekeeping function, may have additional features integrated with it, like the timing management, watchdog function, power on reset, etc. We'll continue the presentation by looking at the NXP's portfolio for real-time clocks. So basically the message here is that NXP has a very wide portfolio of devices, of real-time clock devices, and we have devices that can address different applications, different customers' needs. But for this presentation, basically I've highlighted a few devices that we want to cover. So we're not going to talk about all the devices here, but I want to focus more on those devices that are designed to target very low power applications. So these are the low power real-time clock. We'll talk about the PCF8563, the PCF2123, and the PCF8523. Those are the lowest power consuming real-time clocks in the industry. So we'll talk about those also, and then I want to talk also about the PCF2127A and the 2129A, which have the integrated crystal that I mentioned, and so customers can use those to attain very high accuracy within the system. So let's look at those devices that I mentioned. Let's begin with the PCF2123. The PCF2123 is a very low power and ultra low power real-time clock. It has an SPI interface. So if the customer prefers to use an SPI interface and power consumption is very important, then this is the device of choice. Again, I mentioned earlier that the current consumption is very low. For the PCF2123, the current consumption can go as low as 100 nanoamp. That's measured at 2 volts. That's a typical current consumption. Again, it has SPI interface, and the bus interface can go as high as 6 megahertz, and then some additional timekeeping functions, and a programmable timer. If a customer wants to use a timer in that device, then they can do so. And then there's a clock output also that can output either a 32 kilohertz or there is a divider divider register within the device, and the user can program that register depending on the frequency of interest. Then they can get the desired frequency at that clock output, and then there's a clock enable also tied to it. There is also one feature that's in this device that is really of importance, and I want to highlight that, and that's the electronic tuning feature. So on the next slide, I want to focus more on that electronic tuning feature, which is also available in the PCF2123. The electronic tuning feature is basically a register within the device whereby the user can write some data to that register and be able to compensate for any drift in accuracy in the real-time clock. So depending on the data, on the value that is written to that register, the user can compensate and be able to speed up or slow down the timekeeping, the updates of the second, minute, and hour register within the timekeeping function. Now, why is this important? This is important because with real-time clocks, sometimes, again, the accuracy depends on the crystal, the tuning caps, and sometimes that may degrade also over time. And so to compensate for those drifts in the accuracy, the user can track the device by writing a different value to that register and be able to compensate for the accuracy. So you find this electronic tuning feature being used to adjust for timing accuracy, say during over a long period of time where the accuracy in the device may degrade due to aging of the components around the device. Also, customers can use this register to compensate for accuracy drift due to temperature. So if there is a temperature sensor on board, the customer can, within the firmware, periodically rate the value in the temperature sensor and know at what temperature point the device is running at, and then update that electronic tuning register to be able to compensate for any drift in accuracy due to temperature drift. Then the second thing, the third reason for using this register also is just general accuracy tuning. When you build up a system and you find out from system to system sometimes the accuracy may not be the same, and so during production you can compensate for any drift in accuracy by writing a value to that register. So that's a feature that is present in the PCF2123. I'll also, as I go further with the presentation and talk about different devices, I'll also highlight those devices that have the electronic tuning register within them as well. Let's look now at the PCF8523. So we've talked about the PCF2123, which is a low power real-time clock with SPI interface. The PCF8523 is similar to the 2123. The difference is that the 8523 has I2C interface. So if a customer is interested in an ultra low power real-time clock, but they want I2C interface, then this is the device of choice right here. In terms of power consumption, the PCF8523 consumes as low as 115 nanoamps, and that's measured at 3 volts typical. As I mentioned, again, it has I2C interface, and the clock speed can go as high as 1 megahertz. That's fast mode plus, so it can go as high as 1 megahertz. And then it also has the clock function to be able to keep track of seconds and can measure all the way up to 99 years. And then there's a programmable timer as well, and also a clock output that I discussed earlier. Some features that I want to highlight within this device. I talked about the electronic tuning register that is available in the PCF2123. We also do have the electronic tuning register in the PCF8523, and can be used for the same reasons that we talked about also for the 2123. A couple of other features that I want to highlight within the PCF8523. The first one is the battery switchover function. The battery switchover function basically allows the user to be able to power the real-time clock with either a main supply or a backup battery. That way, if the main supply, if the entire system is shut down, then the backup battery will continue to power the real-time clock, and the real-time clock will continue to keep track of time. And the battery switchover function, the way it works is the device will continuously monitor the power supply, and as soon as the device detects that the main power supply voltage is going down and goes below a certain value, then the device will switch over from the main supply to the backup battery. And there are two ways the user can program this device to operate. There is a standard mode and there is a direct switching mode. The standard mode basically allows the user to program the device so that the switchover occurs at a particular voltage. So independent of what the main supply or the battery voltage is, the switchover will always occur at a particular threshold voltage. And then with the direct switching mode, the switchover will occur when the main supply drops and reaches the battery voltage. And as the main supply goes below the battery voltage, the switchover will occur from the main supply to the battery voltage, to the battery supply. And then to continue with the presentation and looking at the low power devices within our portfolio. Now I want to talk about the low power accurate real-time clock. These are the PCF2127A and the PCF2129A. Both devices have a TCXO integrated within the device. So with using the PCF2127A or the PCF2129A, the user does not have to use an external crystal or external tuning cabs or any external temperature sensor. So all of that is integrated within this device, and the compensation for temperature drift, for the accuracy due to temperature drift, is done within the device. And by doing that, we can achieve a very high accuracy. So the accuracy is as low as plus or minus 3 ppm, which is really good for most systems that require very tight accuracy in the timekeeping function. So on the right-hand side, I'm just showing the first picture at the top. I'm showing how the die and the crystal are integrated within one package. And then the two bottom graphs, I'm showing how the accuracy may vary if they using a crystal which is not temperature compensated. So you can see that accuracy vary with an ordinary crystal as much as plus or minus 20 or even plus or minus 30 ppm. And then with the PCF 2123 and 2127A and the PCF 2129A, because we have the temperature compensated crystal, you see the accuracy curve is a lot tighter there, and we can achieve as low as plus or minus 3 ppm. A couple of features I want to highlight within these accurate real-time clocks. The first thing is that the power consumption also is very low. It consumes as low as 500 nanoamps. That's measured at 2 volts typical. And then also I talked about the Barry switchover function and backup Barry that's present in the PCF 8523. We also have those features present in this accurate real-time clock. And then one other thing I want to highlight also, the main difference between the PCF 2127A and the PCF 2129A is that the 2127A has an additional 512 bytes of RAM. So in case the user needs some sort of a scratch pad or a location to store some data, then they can use the PCF 2127A and be able to do that. Since the real-time clock will be powered on all the time, either from power from the main supply or from the backup battery, then the user is guaranteed that writing any data to that RAM will always be safe. So that the 512 bytes of RAM is present in the PCF 2127A, while the PCF 2129A does not have any RAM. So that's the main difference between the two devices. On the following slide, I'll talk about some additional differences also. And then within these devices also, there's some power management features that are inbuilt in this device. And again, as I said, customers can use this device and be able to eliminate additional circuitry around the board because those features may be integrated within this device. And we'll look at some of those features on the next slide. So on the next slide, I'm basically highlighting some of the features in the PCF 2127A and the 2129A, and then also highlighted in blue the differences between the two devices. So beginning from the top, the devices will operate within the temperature range from minus 40 degrees to plus 85 degrees C, and again have an accuracy as low as plus or minus 3 ppm from minus 15 to 60 degrees C. And then I talked about the difference between the 2127A and the 2129A. The PCF 2127A has 512 bytes of RAM, while the 2129A does not have any. Both devices are available in an SO20 package, and the operating voltage will go from 1.8 volts to 4.2 volts, both for the main supply and the battery supply as well. And then the other things I want to highlight also is the Barry switchover function, which we talk about. Is the ability for the device to monitor the main supply and automatically switch from the main supply to the Barry supply as the main supply drops below either a certain threshold voltage or below the Barry voltage. So the user has a choice to select how they want that to operate. And then there's also the battery load detection function. The battery load detection function is basically a bit within the device that will be set when the battery voltage drops below a certain threshold, and then when that bit is set, there will be an interrupt issue to the microcontroller, and the microcontroller will know that the battery is going low, and maybe send a signal to the user that it's time to change the backup battery. The extra power fail detection function is basically a comparator input, and the user can tie maybe a resistor divider, that input, to monitor a certain voltage. It may be a main power supply voltage or supply voltage to a certain part of the circuitry. And then if that, depending on the value of the resistor dividers that is tied at the input of that comparator, the real-time clock will keep track of that voltage and issue an interrupt to the microcontroller when the voltage drops below a certain a certain point, depending on, and that point is determined by the value of the resistor dividers that is connected to the comparator. So that's just an additional feature that the user can use to be able to monitor certain voltages and schedule certain events based on the supply voltage. And then there is a backup, there's a battery back output voltage. The battery back output voltage is basically what we do is we bring out either the backup, the battery voltage or the main supply voltage to a pin on the real-time clock, and the user can use that voltage to power additional circuitry on the board. So if there's some circuitry, maybe external SRAM, that the user wants that to be powered on all the time, since we know the real-time clock will be powered on all the time, either from the main supply or from the backup battery, then that circuitry may be connected with this BBS pin on the real-time clock, and the user will be guaranteed that circuitry will be powered up all the time, so there will always be power available on that pin. And then there's also the reset output. The reset output basically works in conjunction with the countdown timer. So because the PCF2127 has the countdown timer, there is a reset output present in the PCF2127. The PCF2129 does not have the reset output or the countdown timer, but watchdog function is present in both devices. And then the timestamp is also a function that is present in both devices. The timestamp function, basically the way it works is there is a timestamp input pin, and if the logic level on that pin toggles, then what happens is the real-time clock will automatically read the values in the second, minutes, and hour register, and then write those values in another set of registers that's called a timestamp register. And then later on, the user can come in and read the timestamp register and know exactly at what time that timestamp pin toggle. So this can be very useful if the user want to keep track of exactly at what specific time an event occur. Then if that event occur, that some logic based on the occurrence of that event can be tied to that timestamp input, and then the device will automatically know at exactly what time that event occurred. So those are some features that are present within the accurate real-time clock device, and then also highlighting the differences between the two devices that we offer, the 2127A and the 2129A. Now we'll look at a newer device that we're working on, which is the PCF85063. And this device comes in different versions. Basically, the PCF85063 is a small print real-time clock that consumes very low power. So we've talked about the different devices that are low power real-time clocks with some additional features within the device. But if a customer is interested in a very low power real-time clock and they're not interested in additional features, and they just want a simple real-time clock that consumes low power and keeps track of time, then these are the devices that we will recommend. There are three devices here. There is the PCF85063, and then there is the 063A and the 063B. The 063s and the O63A have I2C interface, and then the O63B has SPI interface. So depending on the interface of choice, the customer can decide which device to use. Additionally, also the O63 has is just, doesn't have any additional feature, alarm timers and things like that. So if the customer wants no additional feature, then they can go with the O63. But if they want the alarm timers within the device, then they can go with the O63A. These devices are, again, very small footprints, very low power consumption. So we see them being used in, applications like printers, copying machines, battery-operated equipments also. Typically in equipments where power consumption is very important or space is, constrained, is also important. We do have samples available, so if, anybody is interested in getting samples of this device, we can support with that. Continuing with the presentation, we'll look at some of the applications for low power real-time clocks, or some of the accurate real-time clocks that we've talked about. I've just shown here some, not all the applications, but just to give an idea of where these devices are being used. Either applications that require very low power or space constraint or high accuracy. So you see in electric meters where accuracy and also power consumption may be important. If the meter is down, if the electricity is down, the meter still needs to retain the information for a certain period of time, and you want to ensure that the devices that are powered on are not consuming too much power. So sometimes you want the real-time clock to consume very low power there. And then also in data acquisition systems, typically when collect data, the data needs to be timestamped to know exactly at what time the data was collected. So you have a real-time clock device in those data acquisition systems, and you find some of these data acquisition systems being deployed out in the field and powered up by batteries. So that's why basically power consumption will be very important in those systems. And then in trucking applications too, where you're shipping goods from one end of the country to another, especially perishable goods, and they need to be refrigerated. You have some tokens in those trucks which periodically wake up and measure the temperature, timestamp the data and store it, and then at the destination, when the truck reaches the destination, the driver can download the temperature profile and be able to tell how if the temperature rise above a certain value and the meat is maybe bad or something like that. So those applications are very important. And then security camera projectors, just showing a variety of applications here where they're being used. My favorite is, smart cards. We're finding a lot of smart cards now using real-time clocks, where basically the password on those cards needs to change periodically, and so it's very important to have a real-time clock that is low power, because the card needs to last typically 3 to 5 years, and so the real-time clock device that is mounted on the card, not only is it a very small size real-time clock, but also needs to consume very low power to be able to allow the card to last a long period of time. And then you find glucose meters also having real-time clocks in them. So just showing it, giving some ideas in terms of where these devices are being used. And then continuing with the applications, an application that will require a real-time clock. One of the applications I want to highlight here is a battery backup application. Typically you see solar green energy is something that is coming up a lot, and you find a lot of energy harvesting systems. So you find a lot of systems that are using solar power or some other form of energy harvesting power from the environment. And within those systems, sometimes the power consumption either within the battery or the power storage device may be very low. We're talking about as low as 5 or 10 microamp hour here. So basically, in those applications, the NXP's real-time clock devices, because they consume very low current, they are very suited for these applications because you can use those energy harvested power and be able to power the NXP's real-time clock, and the device will still maintain its timekeeping function for a very long period of time. So at the bottom right, I've just shown, and on the right-hand side, I've just shown some diagrams here, show how you would connect an energy harvested device, the VDD and ground, to the NXP real-time clock device, and then be able to keep your time that way. And then at the bottom table, showing that depending on the energy storage capacity, as low as 5 microamp hour, you can have the NXP real-time clock device last a very, very long period of time. Because these devices consume as low as 100 nanoamp, even if with a device that has just 5 microamp hour, the real-time clock can last as much as 50 hours there. So that's a lot of time. And now, if you use a device, if you use something that has even a bigger capacity, then you get even more time out of that. And then another application also that I want to highlight is, power savings applications. So we've talked about, basically these devices being used in applications where power consumption is very important. One of the things that is also important is in a system you may have a processor, but you don't want that processor to be on all the time. So maybe what will happen is the processor may wake up maybe periodically and stay awake only for a short period of time, check if it's time to collect data or to do a certain scheduled event, and then it does what it needs to do and then go back into low power mode, and then it needs to wake up again. So you need a very low power real-time clock in order to save energy within the system. You need a very low power real-time clock that will continue to run, and then will be able to wake up the microcontroller when it's the next scheduled event to either collect data or do a certain task. So, because the real-time clock needs to be powered all the time, you want that real-time clock to consume as low power as possible. So that's basically what I'm showing here on this slide. At the right, you see a real-time clock with the interrupt pin on the real-time clock connected to one of the IOs on the processor, so that when it's the scheduled time for the processor to wake up, then that real-time clock can basically issue an interrupt to the processor and wake it up, and then the processor will do what it needs to do. I've just looked at some coin cell batteries. Typically, with a coin cell battery, you can find a coin cell battery that consumes about 20 milliamp hour, or even as much as 30 milliamp hour. And just with the real-time clock running at 100 nanoamp, you can have the battery last in tens of years, so a very long time. Now, with the microcontroller running periodically, that may drop. But the idea here is, with the real-time clock running most of the time, that battery, the battery will not, run out of juice because of the real-time clock. There may be other things involved here, or even the shelf life, or how much current your microprocessor is consuming, and other circuitry other devices within the circuitry. So that covers some of the applications that I want to highlight in terms of real-time clocks. Now let's look at some of the development tools that we offer from NXP. The first is the PCF2123 demo board. We do have a demo board with a part number OM6297 that can be used to evaluate and demonstrate the functions within the PCF2123. That's the low power real-time clock with SPI interface. And then also another tool I want to highlight is the OM11051, which is an evaluation board for the accurate real-time clock, the PCF2127A and the PCF2129A. With this demo board, what we've done is bring out the SPI and the I2C interface. And there are two boards. If you want to evaluate the device using LPC Expresso, then the real-time clock board plugs into the LPC Expresso, and the code is already written in the LPC Expresso to do that. But if a customer wants to evaluate the board with their processor, then what they can do is unplug the LPC Expresso, and they will brought out the I2C and SPI interface, and the customer can connect to those interface pins and be able to evaluate the device and check, the clock, calendar, the different features within the device. And then the last tool I want to highlight, we do have a user manual, which is the UM10301, available on the NXP website, and also an application note, which is the AN10652, also available on the NXP site. And these documents go into details and explain a lot about the differences between the NXP real-time clock devices, how to design these devices, the circuitry around it. Also, there's layout information, also a lot of information about the code, the programming of the registers, and very useful information within these two documents. So if you're designing with NXP real-time clock devices, I strongly recommend having these documents on the site as a guide. In conclusion, I just want to highlight the things that we've covered during today's webinar. So we've talked about, the fact that NXP offers a very wide portfolio of real-time clock devices. So depending on what your needs are, we can work with you and recommend a good real-time clock device that will meet your needs. But, the main thing I focus on in this presentation is low power. So for low power applications, NXP do offer the PCF2123, which is an SPI interface device and consumes as low as 100 nanoamp of current at 2 volts. And then we also do offer the PCF8523, which is an I2C interface device and consumes as low as 150 nanoamps at 3 volts. And we also talk about the accurate real-time clock device, the PCF2127 and the 2129A, which have both SPI and I2C interfaces and consume very low power also. In addition, they have the integrated TCXO that allows those devices to achieve very high accuracy. NXP do offer additional features also within the devices. We'll talk about some of those features, the watchdog, timestamp, RAM, power management features, etc. So this concludes the presentation for the designing with ultra-low power real-time clock from NXP Semiconductors. Mike, I'll turn it over to you for the Q&A session.
Thanks, Emmanuel. We do have some excellent questions coming in, and again, if you have more questions, please use your console window, and we'll get those into the queue. So, okay, Emmanuel, the first question, you talked about the 85063. Question on whether it has an open drain or push-pull output.
The 85063 has the question is not clear. The open drain or push-pull output is that with regards to the interrupt output or with regards to the clock output? The interrupt is open drain, and then the clock also is, I think the clock is open drain. I'll have to verify for the clock output to be certain, but the interrupt output is open drain.
Okay, so if there's any more questions, you can get back to me afterwards.
Yeah, I can make the data sheet available also to the customer, or I can check and get back to the customer in terms of the clock output, but the interrupt output is open drain for sure.
And there was a similar question regarding the PCF2123, asking why does it have an output enable if the output is open drain?
The reason for that is, with the clock output, sometimes even though it has an open drain output, if the clock output is toggling, it still consumes some power. So sometimes in the application, the user may want to go in a very low power mode where they disable that clock output buffer so that it's not toggling and consuming additional power. And that's the reason for the output enable feature there.
Okay. Next question is, what is the lowest power consuming real-time clock that you would recommend for designing into a battery operated piece of equipment?
The lowest power real-time clock, again, it depends on the interface of choice for the customer. So if a customer prefers the I2C interface, then I recommend the PCF 8523, which has I2C interface and consumes 150 nanoamps at 3 volts. If the customer prefers an SPI interface, then I recommend the PCF 2123, which consumes as low as 100 nanoamps at 2 volts. These are the lowest power consuming real-time clocks in the industry, both the PCF 2123 and the 8523.
Okay. Next question, could you talk about some of the power management features that are in NXP's real-time clocks?
The power management features, I highlight those on slide number 12. So some of the power management features, there's the barrel switch over function, the barrel load detection function. There's also the barrel backup output voltage, whereby you can power additional circuitry on the board with the power that is from the real-time clock. And if there's additional circuitry that needs to be powered on all the time, or when the real-time clock is powered on, there you could use that. Then there's also the extra power fail detection function, whereby you can monitor additional power supplies on your board. There is a comparator input that the user can use those to monitor additional voltages on the board and track when that those voltages go above or below a certain threshold, and that information will be sent to the microcontroller for that.
Okay, and question on one of your other parts on the PCF 8564. Question is there an equivalent to that in an SMD package?
The PCF, what was the part number again, please?
PCF 8564. I don't think that was.
Yeah, the PCF 8564. We do have that in bare die. We could make that available in package. What I would want to recommend is maybe the customer can send me. I think, Mike, you're going to make my email address available, right?
Yeah, we'll have, and we'll be able to.
Yeah, I can. We can look into the device that closely matches this feature and available in a surface mount package, and provide that information to the customer. That wouldn't be a problem.
Okay.
Yes.
Let's see. We have next question. Could you just get back on individual part numbers that do not require an external crystal?
The parts that do not require external crystal, the main parts, the two parts I want to highlight are the PCF 2127A and the PCF 2129A. These are the accurate real-time clocks. They do have the crystal integrated within them, and they are already temperature compensated, and so that's how you achieve the high accuracy. But basically, if a customer uses any one of those devices, then they do not need to get any additional crystal on board for the timekeeping function or tuning capacitors or temperature sensors to be able to accommodate for drift due to temperature.
Okay. So this next question is very detailed. Let me read through this. Is it possible to use the timestamp pin and the GPIO or SPI I2C control pins outputs to store multiple events in the RTC? I'm thinking of tying the WDT to the RTC. I'd like to detect the reason for power failure. So I guess first, is it possible to use a timestamp pin and the GPIO to store multiple events in the RTC?
Is it possible to use a timestamp pin and GPIO to store multiple events? So let me make sure I get this right. Multiple events. The customer wants to know if it's possible to know when that timestamp pin toggles, and then for that time to be stored, and then later on if it toggles again for that time to be stored. If that's the question, then no. Let me explain. Let me go into detail and talk a little more about the timestamp feature. So the timestamp register, there's one set of register. So what that means is 2 times cannot be stamped in that register. So you can only stamp 1 time. And the time that can be stamped, there are 2 ways in which the device can be programmed. The device can be programmed so that once data has been written into the timestamp register, no additional data can be written into that register until the microcontroller reaches that timestamp register. What that allows is if multiple events occur, then the micro will be able to know only when the first event occurs. Okay, so that's the first way it can be programmed. The second way is it could be programmed so that if multiple events occur, every time an event occurs, then the timestamp register will be overwritten, right? So if the device is programmed in that manner, then when the micro reads the RTC timestamp register, the micro will only be able to tell the last time that the event occurred. So basically, if multiple events occur, the device can only tell the first time the event occur or the last time the event occur, but it will not keep track of every single event that occurred.
Okay.
I don't know if that addresses the question.
I think it was a very detailed question. I think you could perhaps get back to that.
I think you mentioned also tying the watchdog timer to the timestamp pin. I wasn't clear about that part of the question.
I think it might be better to get back to him after.
Yeah, I think for such a detailed question, what I would want to recommend is if the attendee can just send an email to my email address, then I'll address the specific need here.
Make sure we give that out again at the end.
Thank you.
The next question is, what are my options for a higher accuracy or stability than 3 parts per million?
To achieve higher than 3 parts per million, with the devices that are accurate real-time clock with integrated TCXO, they go as good as plus or minus 3 ppm. Now the devices that do have external crystal, you can still use external crystal and achieve very high accuracy. And basically the ways to do that is, if you're using an external crystal, is either the customer will have to buy a very expensive crystal that has a very tight tolerance, or the customer will have to use a temperature sensor with very tight tolerance and maybe reduce the resolution, that is, read the temperature sensor more often, and increase the granularity in terms of how often they read the temperature sensor, at what temperature range do they accommodate for the drift. So those are some of the ways you can achieve very better accuracy using an external crystal and maybe a higher accuracy temperature sensor, and doing the adjustment more often.
Okay, this question has to do with your slide on battery backup applications, and the question is, could you just provide a little bit more explanation on what does backup time mean?
Okay, this slide on battery backup application.
16.
So the backup time, this is a rough estimation also, but basically what the backup time that is presented here, basically what I've done is say, if you have a battery with capacity of about 5 microamp hour, and the real-time clock consumes 100 nanoamp, then do the calculation to find out at 100 nanoamp how long will it take before the real-time clock depletes all the capacity within the battery. And so that is an equivalent of 50 hours. Now that assumes that it's just the real-time clock running off that battery. If you have a micro connected to that supply, then you have to take into consideration how much current your micro is consuming in the different modes that the micro will be. If you have additional circuitry, maybe A to Ds, AA prom, depending on how much circuitry you have tied to it, then to find out the entire time for the system to deplete that battery, then you have to take those into consideration. But without that information, basically what I did, I said, using NXP's real-time clock, this is how long it would take to deplete the battery. That way, that can be compared with other devices and do apples-to-apples comparison. But basically, that just says with NXP's real-time clock running off this battery, this is how long it takes, for the battery life.
Well, that brings us just about up to the end of our time for today. For those that had more detailed questions, we have your contact information, and we'll get back to you. If you want to send an email to Emmanuel, his name is on the title slide, and his email address is his first name dot last name, emmanuel.nana@nxp.com. You should see a survey on your screen. We'd appreciate it if you would fill that out and provide some additional feedback information for us. And I want to thank our presenter, Emmanuel T. Nana and NXP Semiconductors, for this very informative webinar. The webcast will be posted online at the URL that's on your screen within the next 48 hours. And note that an audio-only podcast version will also be available. And you can search in iTunes Store for embedded_eCast, and you'll find all of Open System Media's eCast there that you can download as MP3 files to play on your iPod. So thanks for all the questions, thanks for attending, and have a great day.
Thank you very much, Mike, and thanks also to the audience for attending.
Okay, bye-bye.